Hello everyone. In today's video I'm going to solve some elementary number theory problems from Sierpinski's book 250 Elementary Number Theory Problems. That book was published in 1970, so it was actually published a year after he died, but anyway. First problem. Find all integers n such that n squared plus 1 is divisible by n plus 1. So, in order to solve this question, first we put f of n is equal to n plus 1, the dividing polynomial. G of n is equal to n squared plus 1. Then we calculate the zeros of the dividing polynomial. So n plus 1 has a 0 at minus 1. We do that in order to find the remainder of the other polynomial by this. So we put the f inverse of 0 in G to get minus 1 squared plus 1, which is 1 plus 1, which is 2. And we want then we proceed to find the integers n such that n plus 1 divides 2. So we want the remainder to be divisible as well as the number itself. There's only one such integer 1, one such positive integer 1, and there's also 0, which is a trivial answer. Next, there's also minus 1 if you count that, but we want only natural numbers, so 1 is the only answer. Then find all integers n such that n cubed minus 3 is divisible by n minus 3. This problem is pretty similar to the last one. So n minus 3 is f of n, g of n is n cubed minus 3, and then f inverse of 0 is 3, and we can find g of f inverse of 0 is 24. So the answer set is all n's such that 24 is divisible by n minus 3. That's range from minus 21 to 27. All divisors of 24 minus 3. Positive or negative doesn't matter here. Third question. Prove that there exist infinitely many positive integers n such that 4n squared plus 1 is divisible by 65. 65 is 5 times 30, so we want 4 times n squared plus 1 is equal to 0, mod 5, and mod 13. So we can find that n must be equal 1 mod 5, 4 mod 5, 4 mod 13, and 9 mod 13. Given that 4 is equal to 4, we can write n as a number 13 times 5 times k plus 4. So it has remainder 4 both when divided by 5 and when divided by 13. That's 65 times k plus 4. For all k, that works, and for all k, it satisfies the equation 4n squared plus 1 is divisible by 65. There are also some other answers, but given that this proves that this satisfies the question that there exist infinitely many such integers, it's a good place to stop. And fourth question. Prove that for positive integers n, we have 3 to the power of 3n plus 3 minus 26 minus 27 is divisible by 169. 169 is 13 times 30, so we can first calculate the number mod 13. That would be 3 to the 3n plus 3 minus 1, and then that would be equal 1 minus 1, 0. So we know that this number is divisible by 13. Now, to get if it's equal 169 or not, we can write it as a two-section fraction. That is, as you can see here in the third line, 2 to the 27n minus minus 2 minus 2 times n, 27 to the power of n, over 13 plus 27 to the power of n minus 1 over 169. First we calculate the number over 13, mod 13. That's 2 to the 27 minus 2 times 27 to the power of n minus 2 minus n, which would give us, oh actually here is a typo, that's 27 to the power of n minus 2n is equivalent of 2 minus 2 minus 2n, which is equal to minus 2n mod 13. Now, in the second fraction, we can divide the divisor by 13 to get 13. Then calculate the mod, which gives us a cyclic group of powers of 27 mod 169 minus 1 over 13, and we can calculate that to be 2n. Exactly, for all n that would be 2n, and 2n plus minus 2n would give us 0, meaning that that fraction would have a remainder 0, and therefore k is an integer. The proof is complete. Thanks for watching.